This is the fourth video about rotation. We'll be looking at a quantity called torque. And we've already established that pretty much all of the linear variables have rotational analogs. And we've found the rotational equivalents of position, velocity, acceleration. We found a way to calculate energy, or kinetic energy in rotation. And we've also found the rotational equivalent of mass. Now we're going to look at the rotational equivalent of force. So first, let's say, well, we know that linear mechanics, F equals ma. And if we look at the equivalent, or the analogous expression for torque, for rotation, it'd be torque equals I, the rotational equivalent of mass, times the angular acceleration alpha. And we know that I equals mr squared, or it's pretty much, that's the dimensions, and alpha is a over r. And so torque we expect to be m times r times a. But ma is force, and so we expect the torque to equal force times distance. And that is precisely what it is, except we need to interpret the distance a little bit. So let's say that we have a pivot point, and we have some particle that can rotate freely around that, and we take a force, and we apply that force, F, at a distance r from the pivot. Also notice that the line drawn between the pivot and the point of application is perpendicular to the force. Now we'll find in this case that the torque, the rotational force that this exerts about that pivot, is in fact F times r. But now let's imagine that we take that same object, same pivot, but this time we'll make the force so that it points in that direction. Same distance r. Now the question is this going to be more likely to spin it or less likely to spin it? If you think about it a little bit, you'll come to the conclusion that in this case, the second case, there is less torque about that pivot. And that's because if you continue the force's direction backwards, we call that the line of action, the effective distance that is from the pivot, right here, we call the moment arm, and we find that the moment arm is smaller. And so this second situation, that force exerts less torque. And that allows us to note that the angle here, so we'll call that r vector, the angle between the r vector and the f vector matters. And we'll find that if we continue the r vector and define this angle between r and f as theta, we'll find that the torque equals F times r times the sine of theta. And that is the definition, or that is how we will calculate torque. It's the rotational analog of force, and it depends not only on how much force there is, but how far from the pivot it's applied, and also what angle it is. Now we're going to learn about a mathematical construct that will help us here. It's something called the cross product. If we have A cross B, that's a way of multiplying vectors in such a way that you get a third vector. This is distinct from the dot product where we multiply two vectors to get a scalar. Sometimes it'll be called the vector product. If you see that, it just means the same thing as cross product. The magnitude of vector c is given by AB sine theta, where A is the magnitude of vector A and B is the magnitude of vector B. And theta is the angle between them. And you might notice that this looks a lot like the equation for torque. Torque equals Fr sine theta, and it just so happens that the vector torque equals R cross F. And that's interesting because it gives the correct prediction of the magnitude of the torque, but it also tells us that torque is a vector, just like other angular quantities. And there's a couple ways of determining the direction of the torque. Now the first way, you point your index finger along the direction of R, the vector that points from the pivot to the point at which the force is applied. Your middle finger, and to avoid flipping people off, you might also point your other two fingers with it along the second vector, the force, and you'll find that the thumb ends up pointing in the direction of the cross product. So in this example here, A and B, you'll find that A cross B points into the page. Now if you do B cross A, so you point your index finger along B first, and your middle finger along A, you'll find your thumb is now sticking out of the page. So B cross A points in the opposite direction from A cross B, so the order does matter. Another way to think about the direction of the torque is if you curl your fingers in the direction the torque will make it start spinning, the thumb will point in the direction of the torque. So, for instance, if we have some particle like that pivoting around here, and we apply a force like that, this object here is going to start spinning in a circle counterclockwise like that, and if you curl the fingers of your right hand clockwise, you'll find that the thumb points into the page, and so the torque in this case would be into the board. Now, if you are given two vectors with magnitude and position, the AB sine theta works quite well. But let's say you're given the torque and the point at which it's applied in unit vector notation, or even better, as components. Then you have this wonderful equation. You do not need to memorize that because it is not going to show up on the tests, but it's a good thing to have, and it will come in useful in almost any college math or physics class. And it is in the front cover of your textbook, just in case you forget it. So, in this example, which is from your textbook, let's say we've got a plumb that is located at the coordinates -2, 0, 4, with a force that equals 6 newtons in the x direction. Well, so we have torque equals R cross F, and that's going to be the y component of R times the z component of F minus the z component of F times, or the y component of F times the R component of Z. That's I hat. I'm not going to say the rest of this, I'm just going to write it. Make sure you get the order right. So But the good news is a lot of these terms are zero. So any term that has the x or the y or z components of f is going to go away. That is 4 of these 6 terms. But now also, the y component of r is also 0, and that means that this whole nasty equation, in this case, simplifies to the z component of r times the x component of f, j hat. And that is 4 meters times 6 newtons, 24 units or newton meters in the j hat direction. And there we go. This is quite useful in 3 dimensions. We don't do a lot of fully 3-dimensional problems in Physics C, but when you do see them, this is quite the best way to do it. And so, basically the torque is the radius times the force, times the sine of the angle between those 2 vectors. Now if you've got multiple torques that act on an object, let's say we've got a pivot point right there, and you've got 2 forces, you've got F1 and you've got F2, and those are applied at distances R1 and R2. The way you define the angles would be like that, theta 1 and theta 2. And so the torque due to force 1 is F1 R1 sine theta 1. Torque due to force 2 is F2 R2 sine theta 2. But you notice that F1 tends to make this object spin in the counterclockwise direction, and F2 tends to make it spin in the clockwise direction, or pardon me, other way around. F1 makes it spin counterclockwise, F2 makes it spin counterclockwise. So you have to make one of them negative. Doesn't really matter which one, you're basically saying counterclockwise is negative and clockwise is positive, up to you which it is, and thus the net torque has a magnitude of this, F1 R1 sine theta 1 minus F2 R2 sine theta 2. Fairly straightforward. And now we're going to use that and apply it to Newton's second law for rotation, which is going to say, not surprisingly, that the net torque equals I alpha. Remember that torque and angular acceleration are both vectors. And it's just like Newton's second law for linear motion. Now let's learn how to apply that. Atwood's machine. Except this time, the pulley is not massless. So the pulley has a certain moment of inertia and a certain radius. And we have our 2 masses, little m and big M. And we know that when we release them, the smaller one will accelerate downward, the bigger one will, or the larger one will accelerate downward, the smaller one will accelerate upward, and there will be an angular acceleration of the pulley. And so to solve this, what we'll do is we'll draw a free body diagram for each mass, where we've got T1 pointing upward, little mg pointing downward. For the bigger mass, you've got T2 pointing downward, and T2 pointing upward, big mg pointing downward. Now, the reason I have to use T1 and T2 here is that there's going to be a net torque on the pulley to make it accelerate, and that means the tensions in the 2 parts of the cord are not going to be equal. And so if we draw what we call an extended free body diagram for the pulley, we'll find that we have T1 pulling down on one side, T2 pulling down on the other side, and some force from the bearing pulling up in the middle. And we'll find that applying Newton's second law to the, so we'll make that direction positive, applying Newton's second law to the 2 weights is pretty straightforward. Find that little ma equals T1 minus little mg, and big MA equals big MG minus T2. That's all old hat. Now for the pulley, though, it gets a bit more complicated. We'll pick our pivot point to be the center, and this is R, and that's also R, which is useful. And so the net torque, I alpha, is equal to T2R, and that angle is 90 degrees, so sine 90 is 1, minus T1R. The reason T1 produces negative torque is that it tends to make the pulley spin in the opposite direction from T2. And so now we have three equations with no fewer than God only knows how many unknowns. But the big thing we want to do right now is relate alpha to A. That's important. But we know that alpha equals A over R, the relationship between the linear variables and the rotational ones. And so now we'll remember all those equations. We'll go to another slide because I'm running out of room. And the equations that I have are little ma equals T1 minus little mg, big Ma equals big mg minus T2, and Ia over R equals T2R minus T1R. And I'll multiply or divide this entire equation by R, so to get rid of that, and move it over here. So we have Ia over R squared equals T2 minus T1. And we have a system of three equations, which is a huge pain in the butt normally. But in this case, it happens to be quite easy if you just add all three equations together. You'll see that T2 and T1 cancel out of both sides. And so what we get on the left side is little ma plus big Ma plus Ia over R squared equals big Mg minus little mg. And then we solve for A. So we get big M minus little mg over little m plus big M plus I over R squared. And now we plug in all the numbers, which I'm not going to show you, and we come up with an equation, or a number, for A that is 0.056 meters per second squared. Now if the pulley was massless, I would be 0, and this would just be like Atwood's machine is in general. So if pulley is massless, I equals 0, and A would be the difference of the masses divided by the sum of the masses times G, which is the simple Atwood's machine. And that means that we probably didn't screw up the algebra. Now that was a whole lot of information, and to help you digest it, you should work questions 8 and 10 from chapter 11, but then also problem 19 in chapter 12, which will help you learn a bit more about the cross product.